In this video, I want to have a look at some of the basic examples of simple harmonic motion. So our first example asks us to consider a particle moving in simple harmonic motion with displacement at any time t seconds given by x equals 2 sine 3t. The first part asks us to sketch a graph of its displacement. So if we're sketching its displacement, there's two things we need to know. We need to know its period and its amplitude, and then we know what shape it's going to be because we know it's a sine graph. So its amplitude is given to us by the number in front, so that's going to have an amplitude of 2, and its period, now the standard period for a sine graph is 2 pi, but we need to divide by the coefficient of t, so we'll have a period of 2 pi on 3. So that means if we draw our graph between 0 and 2 pi, our sine wave is going to fit in there 3 times. Now, this system that I'm using is really difficult to draw these graphs on, so I'm going to screenshot one drawn with graphing software instead. Okay, so this is what our graph should look like. Yours should only start at 0, so you don't need this extra bit down here because we can't have negative time, so we can ignore this whole bit down here. So it starts at 0, it's coming up to 2 and coming down to -2. This does go on forever, but if we just draw it to 2 pi, you can see that that whole sine wave fits in there 3 times. And we should be labeling our axes that that's our t-axis and that's our displacement axis. All right, for the second part, it asks us to sketch a graph of its velocity. So its velocity is going to be the derivative. So if we differentiate this, we know that sine differentiates to cos. So we'd have cos 3t. But we also know that we need to multiply by the derivative of this. So instead of having a 2 out the front, we'd have 2 times 3, which would give us 6. So for this graph, our amplitude would be equal to 6. So we're going between 6 and -6 this time. And our period would still be equal to that 2 pi on 3 because the standard period for cos is also 2 pi. So we're going to fit 3 cos waves in here before we get to 2 pi this time, but our amplitude is going to be much bigger. So again, when you draw your graph, you shouldn't have this bit here. It's just starting at 0. And because it's cos graph, it's starting up here, sorry, not at 0. Time is starting at 0, but our cos wave is starting up here at 6, our displacement, velocity, sorry. Our velocity is at 6, it's coming down to -6 and back up and fitting 3 whole waves in there before we get to 2 pi. Our second example says a particle is moving in simple harmonic motion such that our second derivative, or our acceleration, is given by -4x. For part A, we're asked to show that x equals 3 sine 2t is a possible equation of motion for our particle. So we need to prove that this does satisfy this differential equation. So first, if I differentiate once to find dx dt, we know that sine differentiates to cos, and we have to multiply by that 2. So that would give us 6 cos 2t. Now if we differentiate a second time, cos differentiates to minus sine, and we have to multiply it by that 2 out the front. So we'd have -12 sine, not cos anymore, sorry, sine 2t. Now we can split that 12 up. We could have a -4 times 3 sine 2t. And this whole chunk here is what we started with. That is x, our displacement. So that will give us -4x, which is what we were aiming for. Part B of our question asks us to write down the amplitude and period of motion. So we're looking at this displacement function here. So the period of that wave is going to be given by 2 pi divided by the coefficient of t, which is 2. So our period will just be pi. And our amplitude is given by the coefficient out the front, so our amplitude will be 3. For part C, we're asked to find the maximum speed at which the particle is travelling and the displacement at that time. So to find the maximum speed, we know that speed is related to velocity, and we know that our velocity was 6 cos 2t. Now if you look at this function, the amplitude of that function is 6, so it moves between +6 and -6. So that means, therefore, the maximum speed would be 6 meters per second. Okay, so we found what the maximum speed is just by looking at the amplitude of our velocity function. But then we have to find when that happens and what its displacement is at that time. So we need to find t to give us a maximum of 6. So we're going to set v equal to 6. So we'd have 6 equal to 6 cos 2t, which means that we'd have cos 2t is equal to 1. And that means that 2t would have to be equal to 0, 2 pi, 4 pi, and so on. And that's looking at the graph of our cos function, which would mean that t would have to be equal to 0, pi, 2 pi, and so on. So these are all of the times when it's going to hit that maximum speed. And we need to find its displacement at that time. So x is equal to 3 sine 2t. Now if we substituted 0 in here, we'd have 3 times sine of 0, which is just 0. So at t equals 0, x would be equal to 0 as well. If we subbed in pi or 2 pi or any of these other values for t that we've got down here, it's always going to be 0. So therefore, displacement is 0 meters. So that means that the speed is always going to be the greatest when we are at that equilibrium point. So that's having a look at some basic examples of simple harmonic motion.